Okay, everyone. It's my pleasure to introduce Tess Smidt, 2018 Luis Alvarez Fellow in Computing Sciences at Lawrence Berkeley National Lab. She earned her PhD in physics here at UC Berkeley, working with Jeff Neaton up at Berkeley Lab's Molecular Foundry. During her graduate career, she spent a year as an intern at Google's Accelerated Science team, where she applied the company's machine learning tools and expertise to tackle the problem of encoding 3D rotation equivariance into neural networks so they can naturally handle 3D geometry and properties of physical systems. She is currently designing a neural network that can automatically generate novel atomic crystal structures. I'm sure we're all very excited to learn everything about Tess Smidt today, so please give her your full attention. Tess, thank you so much for being here.
Thank you. Thank you for the introduction, and thanks for having me. My name's Tess. So I am a postdoctoral fellow up at the National Lab. I just graduated in May. So just to get a sense of who's in the audience, how many of you are undergraduates? I hear we've got some of you guys. Cool. And how many of you are graduate students? Okay, a lot of graduate students. Any postdocs? All right, no postdocs. I mean, postdocs are great, but like all grad students. Okay, great. So I got to explain this title a little bit. So So for the fellowship that I'm on, usually they will interview you just to have a little blurb on the LBL website. And so I was explaining to the science writer, she's like, okay, well, tell me what your research is. And I'm like, well, at parties when I'm with non-scientists, I usually say I'm an atomic architect. I like to design where we should put the atoms to kind of produce those interesting properties. And this sort of catchphrase seems to be catchy enough that it's been following me around. So that's there. So today in my talk, I want to give you a bit of kind of an overview of my research in deep learning, applying deep learning to atomic systems, just to give you a sense of, okay, what does maybe a research program in material science and deep learning look like? But then I really want to open the floor for questions so that we can, I can talk a bit about my PhD, like how did I choose my projects during my PhD? How did I end up at Google for a year? What was that like? I actually was deciding between becoming a postdoc at the National Lab or taking a research scientist position at Google. So I had the two offers on the table. If you are curious how I made that decision, we can talk about that too. And really just any questions you have that come up from the talk. So feel free to raise your hands if you have questions. This is supposed to be really low key and informal. All right. So research. Yes. So my background is that I'm a computational materials physicist. So there's many other people in the room, I think, who are also computational materials physicists. But one of the things we do is that given an atomic structure, so this is the crystal structure for silicon, I use quantum theory and supercomputers to determine, for a given set of nuclear coordinates, where are the electrons at and what are they doing. So in this top diagram here, I have an electron charge density showing me sort of where that the electrons in silicon are concentrated between silicon atoms. And here I have what's called a band structure diagram, or more lovingly called a spaghetti plot by practitioners of the field. And what this is showing is it's showing the relationship between energy and momentum of electrons in the silicon crystal. So basically, if you see really bendy bands, that means it's very easy for the electrons to move in the material. And if the bands are really flat, they're really not doing much. And these types of diagrams help us assess, like, okay, how much energy does it take to go from one energy level to the next? And kind of, see what material properties this thing could have. It's a little bit like reading tea leaves, so there's a bit of a learning curve, but they're very useful. So when I do these types of calculations, I don't just do one calculation at a time. I like to do thousands at a time because that's like way more fun. And to do that, I use something called workflows, which are basically recipes that automate best practices for performing these types of quantum mechanical calculations. And you can use these types of calculations to screen for specific material properties and see if they might be good for particular applications. So if I have a structures database with tens of thousands of structures, I might assess various properties that they have, elasticity or band gap, electron mobility, and whatnot, to assess whether they might make good photovoltaics, battery materials, and so on. So this is pretty great, and we're getting really good at doing high throughput density functional theory and quantum mechanical calculations, but there's a problem. So this screening is bottlenecked by our ability to propose hypothetical atomic structures, which basically means, oh, sorry, was there a question? No. So the materials in existing databases that we do screen are usually things that we've seen in the lab, things that we've measured, things that we know exist. Then we can sort of change it up a little bit by doing small modifications or elemental substitutions. Like, okay, instead of iridium's expensive, maybe I want to try rhodium or something. Well, rhodium's still expensive, but you get the idea. So you can do small modifications of these structures and then put them into your high throughput pipeline to screen maybe these ones will have a better chance. And since we already know how to make one, we can make this other one. But we're really missing are like new geometries, things we haven't necessarily seen. And these materials might have really interesting properties that might surprise us. And only when we include all these structures can we really say, hey, like I found like the top 1,000 candidates as a photovoltaic or whatnot. So it'd be really useful if we had this. And you might be saying like, well, hypothetical structures from, a computational theorist, like I don't know if I trust them. Like, do we really want hypothetical structures? But the thing is, people are making new structures all the time. Experimentalists are making things every day that have really surprising and interesting properties. And like as theorists, don't we want to be kind of ahead of them on that, and instead of just lagging behind and helping them understand the given materials that they're seeing in their lab? So these are two examples from my PhD research. These are harmonic honeycomb iridates, which have exotic frustrated quantum magnetism at low temperatures. And then there's these metal organic chalcogenide assemblies, which are self-assembled, meaning pretty easy to make, bulk materials. So they're three-dimensional, but they have low-dimensional properties. So super interesting. You don't have to exfoliate it to one layer for it to have sort of quantum confinement behavior. You just get it from how the crystal is structured. So these are really cool. Like I would love to be screening for materials like this in my pipeline instead of waiting for experimentalists to be able to characterize them. So you might say like, okay, well, how do we go about designing materials? Turns out it's really hard. So I've tried it by hand for a lot of things. I have a bit of a background in architecture, and so I put my use of parametric models to the test, and I would take these little like subunits of transition metals and sulfur atoms and various molecules and try to piece them together. And I was like, oh, if I can twist it this way, I can alter the band gap and things like that. Or, oh, if I take this 2D sheet and actually wrap it into a nanotube, like maybe that'll give me interesting properties. And like this is a fine way to go about things, but it's not very automatable and it's not very systematic. What we really need are better design tools to generate new hypothetical atomic structures. So this is where I think deep learning can come in. So deep learning can help us in several different ways for automating computational, chemical, and materials discovery. So it can help us predict properties faster. So these density functional theory calculations that I keep talking about using supercomputers, like it takes a lot of computation to do it. Can we have neural networks that can do it faster and maybe with accurate enough calculations that we can use them for screening? Then the one thing that I'm really interested in is being able to generate new structures based on things we've already seen in the lab. So generating hypothetical structures based on existing patterns. And then sort of the holy grail of computational materials discovery is you give me a set of properties you want and I give you a structure. But I would suggest that we probably need to be able to generate any structure whatsoever before we generate sort of tailored couture properties. Okay, so just to show that I'm not crazy, I'm going to show you what's in the existing literature of what people have done so far. So people have actually demonstrated that you can train neural networks to basically predict properties that come out of quantum mechanical calculations. And they can do it with the same level of accuracy, about 2 to 5 orders of magnitude faster. Now, of course, there's a couple asterisks on this. Typically, these models are trained for very specific materials. So here's 3 different papers that I just wanted to mention, because I think they're really good examples in this area. So the top one, this is a paper put out by Google Brain and the Accelerated Science team a while ago, where they were predicting various quantum mechanical properties of small molecules. This is the QM9 data set, which consists of carbon, nitrogen, oxygen, maybe some fluorines and things like that. So very simple small molecules, but they were able to use a graph representation of the molecules and to predict these properties. Then this one down here, this is from Jeff Grossman's group at MIT. They used a similar sort of a graph representation of crystals in order to predict properties such as energy and so forth. And then finally, this one just came out of Vijay Panda's lab at Stanford. And what they did was really interesting. So they would use a very cheap quantum mechanical calculation to calculate the electron density, so where the electrons are at for actually the same data set that the top paper used for this QM9 data set. And then what they did is they would train a neural net to take that kind of low-level theory charge density and convert it into a high-level theory charge density. So basically like refine it according to a higher level of theory functional. So that's sort of interesting. People have also used deep learning techniques to generate new small molecules sort of with applications in mind in medicine and in organic LEDs. And they were able to like learn representations of these molecules where you learn a representation that's a little easier to manipulate than manipulating just raw atoms. This top architecture is called an autoencoder, and I'll talk a bit more about it later in the talk. But basically, you take something, in this case a smile string, which is a string representation of the topology of a molecule. It encodes it into a vector space, so this kind of continuous representation of molecules. And then it's able to spit it back out. So you're able to encode and decode. And what's useful is that you can use the middle part to either do some sort of optimization, because it's a lot easier to optimize over a vector space than it is a bunch of atoms. But you can also optimize molecules that are generated using something called reinforcement learning, and that's what another paper did more recently. I think this came out this year, where they trained a model to be able to generate valid smile strings, so these string representations of molecular topology, and they were able to give it rewards for like, oh yes, that one looks very drug-like, please generate more. So that's sort of the state of the field right now. So one thing I want to emphasize from these examples is that basically, all these examples use different input representations for the atomic system. So we had someone using images for electron charge density. We had people using strings for molecules, people using graphs showing the connectivity of like sort of bonding for both molecules and crystals. And I want to emphasize that, you know, how to actually represent an atomic structure to a neural net is an open question. This is actually a very rich area and up for much debate. And to maybe illustrate this a little bit further, I'll give an example of how can we encode benzene. There's many ways we can encode it. You could imagine, you know, performing some algorithm and saying like, okay, this has an aromatic ring. I'm going to put a 1 in the first entry in the specter, and then oh, it has 6 carbons. I'm going to put a 6 in here. So you can imagine like sort of building a fingerprint, some sort of way to identify features of this benzene molecule. So, and vectors are great because machine learning methods love vectors. Vectors are easy; they eat them for breakfast. So that's one approach, and it's super popular in cheminformatics and materials informatics. Is to sort of fingerprint your material or your fingerprint whatever atomic system you're looking at. You could represent a benzene as a smile string. So this is just a string encoding that has molecular properties. One reason why this is so popular in deep learning right now, like why you're seeing so many deep learning methods being applied to smile strings, is because we have things that can process strings in natural language processing. So things that process text and things like that. We have those methods already there. So it's sort of an adjacent, it's a familiar representation. So I actually am pretty convinced that one of the reasons why we're seeing so much more advancement in molecules, small molecules rather than other types of things is partially because it's just a representation that can work with networks we already have. You could represent it as a graph of bonds, you could represent it as an image, but you know, all these gray pixels, it's kind of dead space, so it's a very sparse representation. Or you can deal with 3D coordinates. And you might ask, okay, which one's best? I always like knowing what's best. None of them are best. You always sort of lose something. So if you really care about bonding, if bonds are important to you, first of all, it probably means you're a chemist. But you know, smile strings or graphs are like, that's a pretty good way to represent things. If you want geometry, you know, images and 3D coordinates, you really can't beat that. Okay, maybe you want to throw bonds in there, you can do a mixture, but then it gets more complicated. Some of these methods are very memory efficient, some of them are not. So as you can imagine, all that dead space for the image of the benzene, like it's gonna kill you in 3 dimensions. And then this last one, which is sort of the one I want to harp on because I think it's very important, is universality. So does this representation only apply to some types of atomic systems, or does it apply to all of them? So let me give you an example. So let's say in my data set I have a benzene molecule, but I also have a molecular crystal of benzene. So some of these representations, it's really hard to extend. So smile strings don't extend. You might be able to adapt your fingerprint and graph of bonds, but then your graph's including van der Waals interactions, and it's kind of not clean for how you do that. But images and coordinates scale pretty, you know, it's very clear how you sort of extend that. You either make your image bigger, or you just add in more coordinates. So, you know, they seem like, okay, these are pretty good. Well, they come with their own problems. So if you end up dealing with things like images or 3D coordinates, there's 2 properties that you sort of want your network to have. And they have fancy names, but I'll break it down. So translation equivariance and rotation equivariance. So translation equivariance means if I was able, let's say I have an image of bunny rabbits with their tongues sticking out. Very common task. People think it's all about cats, but it's actually about the bunny rabbits. So I have this image of a bunny rabbit, and I've trained my network to be able to identify bunny rabbits in this part of an image. Well, you would hope that if you did that over there, it should be able to recognize if I shift the bunny rabbit over here. So basically, if I shift something, if I change sort of my origin, if you will, coordinate transformation, this shouldn't mess up the predictions of my network. So that's sort of what it means to be translation equivariant. I can still recognize the bunny rabbit, but I can also see that it moved. And then rotation equivariance is similar. So if I have a rabbit and it's kind of oriented up and down, if I turn the bunny rabbit, I can say, okay, that's still a bunny rabbit, but now it's rotated. So the next thing is translation equivariance comes with convolutional neural networks, which you may have heard about. They're probably the most popular type of neural network out there, really good for image processing. You basically have a learned kernel, kind of like a little filter window that you scan across the image. And the reason why you get this property is because you're using the same weights on all parts of the image. So that's how you get this property. But rotation equivariance, no one had really dealt with it until about 2 years ago. And that was only in 2 dimensions. 3D, it was unsolved. And so the way that people deal with this is that they typically do data augmentation. So they'll take pictures of bunny rabbits or cats, and they will basically make a bunch of additional versions of it, maybe 10 or 20 copies of it in different rotations, and train the network on that. So it has to learn additional filters to be able to identify that. So it's not a very elegant way of doing it, but it certainly works in computer vision. Another way to do it is that you could try and restrict the information you use in your filter, like you could just use radial information. So rather than using the fact that this pixel is this far away from me and over here, you just say, I just know that this pixel is this far away from me. And then everything in your network only knows about distances, which is rotation invariant. If you rotate something, the distances between things always stays the same. But it's kind of a patch, it's not a fix. And so ideally you want a network that is able to preserve both the geometry and symmetry of your problem. And I think this is particularly important for atomic systems because the laws of physics have these symmetries encoded in them. So, and kind of an especially big reason why I think this is important is that, in crystal structures like the one I'm showing here, we might have these sort of like octahedral motifs, and they'll be in different orientations, and it'd be really nice if we could use the same filters on both orientations, both locations. So if you have these properties as part of your network, you can do this. So we fixed it. So as I said, other types of representations sort of have certain problems, and a lot of networks throw away a lot of potentially useful geometric information. And so first my friend Nate and I, we figured out kind of the math for this network. But then I was at Google, and I'd actually finished my first research project early. I finished it in the first couple weeks. And then they're like, oh, well, you have to work on something else because you still have more of your internship. And I'm like, well, my friend and I had this idea. Can we bring in this math for this network, and can we build it here at Google? And they were very kind, and they said, oh, yes, of course. And said, well, we also want to take you back with us. And I'm like, yeah, no problem. And so the Google Accelerated Science team was awesome and let me work on this for my internship and then for my second internship. So we created this framework that it's a convolutional neural net that has 3D rotation equivariance built into it. This is our paper. We call it tensor field networks for reasons that I'll explain on the next slide. But so usually when I give a talk, I'll give a 1-hour seminar just on how this network works. Obviously, I think there's other things that we might want to talk about. But the TLDR of it is we built basically a convolutional neural network. The features, there's 2 things that differ though. So, we operate on points instead of images, but that's kind of a minor detail. The filters, rather than it just being a learned filter of pixels, our filters take a specific functional form. It has learned radial functions, and then it has specific angular functions, which are the spherical harmonics. Now, if you remember solving for the hydrogen atom, our filters have a very similar form, except for we're learning the radial function. It's not a fixed radial function, but we use the spherical harmonics. And the spherical harmonics look like this. You might recognize them as the s, p, d, and f orbitals. Now, you can actually take L to infinity. These are just the ones that you're most used to seeing. The spherical harmonics are indexed by 2 numbers, L and M. L is sort of like the angular frequency. And then for a given angular frequency, you have 2L plus 1 spherical harmonics. And they have a lot of really nice properties dealing with 3D rotations. So that's the basic thing, but that's not all. You might think, okay, So you change your filter, big whoop. Turns out this has consequences for our entire network. So everything in our network ends up becoming a geometric tensor. So scalars are tensors, vectors are tensors, 3x3 matrices are tensors. So everything in our network suddenly carries this additional context that it transforms predictably under 3D rotations. This means that everything in our network, so not just our filters, but the input also carries L and M indices. And this makes things a little complicated because then you might ask, okay, I've got this tensor and this tensor. If I want to combine them, I just multiply them, right? Not really. And the reason for this is that you actually need to obey something called tensor algebra. So what is tensor algebra, or more generally, what's a tensor product? I found a really cool infographic about this, actually, so I'm going to show that. What's a tensor product? Okay. Let's say you have a scalar and you have a vector. You can multiply them. Now it's like a bigger, smaller vector. Huzzah. But now let's say I have two vectors. What does it mean to multiply two vectors? We've got dot products, we've got cross products, we've got outer products. And so a tensor product is sort of the generalization of the outer product for vectors of arbitrary dimension. And so kind of the TLDR is we use spherical harmonics, everything in our network's a tensor, and so we have to use tensor products. So it's a bit of mathematical machinery. To kind of more concretely drive home what this network can do, I just want to give this quick example. So this is sort of the unit test for our network, because you can prove that all the math is right, but if you coded it wrong, the network's not going to do what you want. So this is how we check that we coded it correctly. So we trained our network to classify Tetris pieces. It's kind of a fun thing. So in 3D, there are 8 Tetris pieces. And we represent them just as points at the center of the cube, so you'd represent it as 4 points for each of them. And we showed our network only these Tetris pieces in one orientation, so one at a time in one orientation. And then the way we test the network that it has rotation equivariance is that it has to be able to perfectly classify these same Tetris pieces in arbitrary orientations and translations. And this is how we check that, in fact, it can now identify these pieces no matter how they're transformed, and so it's able to do that. And there's a bunch of other little toy examples of other things we did to this network in our paper. Oh, and then I want to emphasize, you might think, well, what about radial distances? So if I look at the various radial distances between one point and another, I can actually distinguish these pieces, right? And that's true except for these two pieces because they're chiral, they're mirror images. So if you look at all the pairwise distances of these chiral pieces, they're identical. The only way to tell them apart is to basically see that one goes this, basically you need you need angle information and orientation information. So our network is able to show that it has this information. All right, so the next thing I want to talk about are autoencoders. And the reason I want to talk about autoencoders is because this is what got me into deep learning. Autoencoders were just they weren't just coming out, but they were starting to become more popular in the deep learning literature. And what I thought was so cool about them is it's semi-supervised learning. You don't necessarily need a data set of I have a data set X with labels Y. Instead, it lets you learn trends in data that are just in there. And so the basic idea with an autoencoder is that you have sort of a recognition and encoding layer for a given input. You have some latent space that we'll talk about in a bit, and then a generation layer. So you can use this as a generative model, which means to generate more examples like your training data, which is useful. And the key thing, you want the input to look like the output to look like the input. You might say, well, that's kind of weird. How do you learn anything? Why don't you just learn okay, copy image, give it as output. So the way that you make it learn something that's non-trivial, meaning not the identity, which is what it would be just passing it through, is you can do two things. So traditionally what's done is that you make this latent space really tiny. So let's say I have an input image, and it's maybe it has 1,000 numbers. And I make my middle layer only have maybe 5. So somehow it has to learn some non-trivial compression of my input data to map it to my output data. That's one way to do it, and that's a traditional autoencoder. Now, there's a new way of doing this. It's called a variational autoencoder, where instead you basically say, okay, I want you to take this input data and I want you to learn some transformation that turns it into a specific probability distribution, so that when you map all your data points into this latent space, it looks Gaussian, or it looks like some other distribution that you want. You get to choose whatever distribution you want it to look like. And there's a lot of nice features of variational autoencoders. They tend to learn kind of representations that are very smooth and have interesting sort of features of that learned latent space. So here's some concrete examples. This is MNIST. So MNIST is a handwritten digit data set. I think probably if you've ever been to a machine learning talk, you maybe have seen this. So basically, this data set was sort of proposed as a way to solve the identifying postal codes on letters. And so what someone did is that they basically made an autoencoder that encodes the MNIST data set, which is a 128 by 128 image data set, into a two-dimensional latent space, so going from lots of dimensions to two. And what I'm plotting here, or what's plotted here, is if I march along the latent space in these two dimensions, so blink, 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 and then I generate output from each of those points, and then I show them here, this is what I'm showing. So what you can kind of see is that this is interesting because one dimension here sort of looks like the swirliness of swirliness of a digit. It sort of has semantic meaning, and if you go this way, it's sort of like how tall and skinny is my digit. And you can also see that there's sort of nice separations between numbers. Like you can kind of see that ones turn into sevens, sevens turn into fours, and so forth. So this is kind of interesting. It didn't tell it to organize it anyway. It just told it, I want you to learn something that's two-dimensional and is smooth and maybe looks Gaussian. And this is what you can get. Here's another example. So this autoencoder was trained on faces. And what's interesting is they didn't try to do this, but they were looking at their latent space, kind of poking around and saying, okay, I'm going to turn this image into this image. What does this direction correspond to? And they found that specific directions actually corresponded to like making the person smile more or smile less or adding eyeglasses or removing eyeglasses. In fact, I think one thing that got some popularity on like Twitter was that like there's some joke that Kanye West never smiles, and so they put his face into the thing and they cranked up the smile vector and posted it or something. But anyway, so you can see that like these learned latent space, even though it wasn't told to learn what the smile direction is, sometimes interesting trends can come out of the data just by having enough data and training a model well. So this is really interesting because, what if we could do this for atoms? Wouldn't that be cool? So an autoencoder trained on atomic systems would actually solve a lot of problems at once. So one thing is that we could actually, maybe have a standardized way to encode atomic structures for general machine learning problems, that I could take the geometry of my structure, encode it into a vector, and these could be pre-trained layers, meaning, so I train a really good autoencoder, and then I can crack that model in half, and I can hand the encoding part to you, and you're like, okay, I care about battery materials, I care about photovoltaics, and then you can train some additional layers that help you train to predict those properties, but you don't have to worry about how you're encoding it. So this is sort of something that could be used by anyone. Another thing would be to generate structures from the latent space. So you can go poking around, maybe you find some interesting directions where you're like, I want something that's like this structure, but I want it a little different. And you can actually articulate what a little different means in a continuous vector space. So that would be useful, and then we can check if we've seen it before, and if not, we can maybe do some DFT calculations or throw it into another neural network to assess its stability and then record it as like, okay, here's a new structure that might be interesting that we can screen for properties. But lastly, I really want to see this latent space, because it would basically be a materials map. It would basically help us assess, like, okay, what does it mean to, like, say, how similar are silicon and, I don't know, this battery material? Like, what does that mean? So you would sort of get a similarity metric with it. So that would be pretty great. Obviously, like, we don't have this yet, but it would be really great if we did. And so this is what I work on. So I want to make an autoencoder for discrete geometry. And so typically neural networks work on images and things like that. So dealing with discrete geometry, there's not a lot of literature on it. So that's what I work on. And essentially what we want to do is we want to basically take this geometry and reduce it to a single point, to a trivial geometry that has a big feature vector. We want to convert geometry into feature vectors and then be able to go back again. And in order to do this, I think what we're going to have to do is sort of look closely at the structures that we're interested in and notice that atomic structures have a lot of sort of geometric motifs that they're built of. So you'll have an atom, it's coordinated by other atoms, maybe in the pattern octahedron. Those octahedron might share edges, and then those edge-sharing octahedron might make a honeycomb network. So sort of taking note that all the atomic structures we're interested in sort of have these geometric patterns. So how do we go ahead and encode local geometry, collapse points down, and then kind of do the same thing and continue to collapse points down until we get points? So this is sort of my current approach. We now know how to encode geometry because we can use these tensor field networks that I talked about, but there's still a lot to do for like how do we start encoding hierarchy. I have some ideas, but it's all work in progress. So this is what I'm up to, and I think that's all for my talk. So that's sort of the research version of what I'm up to. What are we at? So we're at 4:40. I mainly just want to open it up for questions. So if there's any questions on this or anything, otherwise I can give you just a bit more of my background. Yeah, so how did I get to be talking in front of you? I'm going to put this up more as a background than anything. So this is the table of contents for my thesis, and I was more surprised than anyone that when I looked at it, I'm like, man, it sounds like I really knew what I was doing. It's like fancy titles. It looks like everything, especially when I was writing my introduction. Oh yes, all these topics, clearly it was well planned as to how these topics would connect together, such that I could write this beautiful intro for my thesis. And it's like that couldn't be further from the truth. So I actually started off as an experimental particle physicist. I worked on neutrino experiments, and I also worked at CERN in undergrad. And then when I came here, I'm like, oh, no, I want to do real things. And so I'm like, I'm going to be in a materials lab, and I'm going to make things. And I was in a solid state physics lab, and I made materials by crushing things in mortars and pestles and putting them in industrial version of easy bake ovens. And that was really hard. Like, solid state synthesis is really hard. Do any of you do that? Like, it's really hard. And then I was like, oh, I kind of missed computers. We used a lot of computers in particle physics. And so I found Jeff's group, and everyone was awesome there, including these newbies here, these youngins here. Stephanie and Jonah are both in Jeff Dean's group, so you can ask them about it. Like, shout out, yeah. And so then I worked on the theory. But I don't know, so the only two chapters in my thesis that are at all related to each other are the first two, and that's because I did the experiment side and the theory side. And then, come around third year, I had sort of an existential research crisis. I'm like, I don't want to work on iridates anymore. I worked so much on iridates. I don't want to see these materials ever again. In retrospect, it was a really great project, and I learned a bunch of things. But I was like, gosh, what am I even interested in? So I don't know if there's any third years in the audience or other people who might be having an existential research crisis. You're gonna power through, and you're gonna be awesome. My main advice is listen to your gut. Like, if there's something you feel like, I should be interested in this because other people are interested in this. No, you should be interested in what you're interested in, and they can be interested in what they're interested in, and everyone's awesome, and there's enough science to go around. So for me, I liked to code, and I missed a lot of coding, and so I kind of, as I was mulling over what did I want to do next, I also felt, I felt a little distant from other grad students. I felt a little alienated. I'm like, gosh, I don't really know what other people are working on, and maybe that would help me decide what I want to work on. So like any person who knows how to code, I tried to solve some social problems with code. And I ran this thing called the lunch experiment, again with my co-author at Stanford, Nate. We ran this thing called the lunch experiment, and it was randomized controlled lunches for grad students. And it was I don't think any of you guys were in it. Well, you were, okay. I think there's a lot of young faces in the group. So I don't know if you guys know this Dos Equis reference, but like I don't always drink beer, but when I do, we kind of copied that. And I don't always eat lunch because grad students don't eat. But when I do, I prefer the lunch experiment. And it was an automated system, so you would sign up with your email, and it would give you an email invitation. It'd say hey, you're invited to lunch at this time in this place. And you would say yes or no, and it tried to optimize invitations for diversity of majors. And this was really fun. We had about 400 grad students. We had someone in folklore. I didn't even know you could major in that. And we ran about 100 lunches, and that was really fun. And then eventually research started picking up, and I ended the lunch experiment. But in the process, I learned a lot about how to use databases, how to deploy things to Heroku. My Python coding got somewhat better. It got a lot better at Google, I'll tell you that. They have code reviews. But that's an example of something I did. And then I went ahead and I ended up working very closely with some experimentalists on these kind of self-assembled, low-dimensional physics, but bulk 3D structures, and that was super fun. And then I also got to learn a lot. So then I worked very closely actually with Anubhav on this ferroelectric workflow, where basically one of these workflows that we made was to determine whether certain materials had ferroelectric properties. And I got to learn how to do high throughput, and that was super useful. That also really improved my coding skills, and also Anubhav is just awesome to work with. He is just such a clear thinker, and I think he's awesome. And then somewhere around here, I started thinking, well, these workflows are really great, but like, how do we design things? Because there was a lot of times where I really wanted to design these like self-assembling structures, but it was really hard. I couldn't have good design tools, and so I said, this deep learning stuff is kind of picking up. And the first class that they taught in deep learning happened to be the semester I was kind of thinking about this stuff, and so I took that, and that was super useful. So basically, like, I was getting really interested in this stuff. I actually want to mention this. So I was about to say, like, read up on the Cracking the Coding interview. You gotta teach yourself like undergrad algorithms for the interviews, and that's the only reason why you need to do it. It's really its own skill set, and you have to practice. But a combination of that and this is the course in spring 2019. I don't know if there's spots open, but if there are, you should really take this course. It's taught by John Canny. He's awesome. It's a really great course. I learned so much. So between doing that, I was able to get a Google internship. But I want to note that was not the first time I applied to Google. I'd actually applied to Google about a year before, 2 years before, during my research crisis. I'm like, oh my gosh, get me out of here. I need to check out industry. It didn't quite work that time. I had a bit more of a plan for why I wanted to be at Google this time, and it worked out a little better. But if you are at all interested in industry internships, I would really highly emphasize you try it, because it's so much easier to try it as a student than to try it for a profession, because then you have to be there for a year. And you won't necessarily know yet whether you like it or not. So it's a great way, go there for 3 months, kind of learn what it's about, get beefed up coding skills, have something shiny for your resume. And it's also a super fun place to work, and there's just people doing so many interesting things. And then we wrote this paper, and then I graduated. It was pretty good. So I'm just gonna leave this up here. And kind of open the floor for questions. I guess we only have 15 minutes. But yeah, I hope that was useful, interesting stuff. So up to you guys. All right. Is anyone thinking of maybe applying to Google? Or like, are there any people want to hear more about Googly things? Or?
So I have a question regarding that. So how long were you there? You're a year?
So basically I initially had a regular 3-month internship, full time. So I was at Google for a summer. It took some convincing to get my advisor to get on board. The first time I applied, he was like, what are you doing? That is not good for your PhD. No. And then the second time he was like, okay, you can go. He was fine with it. So part of it is just I think a lot of professors are not used to material science or physics students having internships, but in computer science it's totally normal. And then because we had this project going on with this tensor field networks, they gave me a second internship. I had to take it part-time because I had to write up my thesis. And so I was actually a grad student and an intern at the same time, which, I don't think Jeff was thrilled about it, but he was fine. He's like, okay, well, it's your last year, that's fine. And that lasted for an additional 9 months. And that was enough time for me to interview and make my decision between being up at Berkeley Lab and being at Google.
So taking internship is basically pausing your graduate degree?
Yeah, exactly. Yeah, it's basically putting things on pause, but your research will still be there when you come back. So it's I don't know, there's a lot of pressure of oh, I gotta do this now, I gotta do this now. You know what? I had something that people thought was on fire, and then I left for 3 months, and it was still there when I got back, and no one had scooped us or anything. So usually it's 3 months is not that much time, and it's really worth the investigation of whether it's something that makes you happy or not. So, sure.
And how did you decide to come to Berkeley Lab instead?
Sure. So part of it is my specific research direction. I really liked the team I was on at Google, the accelerated science team. They're really great, and I was basically working on material science problems at Google. But the thing is that, if you're solving science problems, it's really good to be close to the other people who are solving science problems to make sure that you don't that you're checking in that what I'm working on is the right direction. And I really enjoy talking with experimentalists and people who do synthesis and things like that. So I wanted to be closer to the problems I was solving. And Google has immense computational resources. The programmers are superb. Everyone's really friendly. But I don't know, you can't really beat kooky scientists when it comes to creative ideas and all their random knowledge that they know and how passionate they are about their specific problem. So I wanted to be more around that. Also, I figured that the postdoc opportunity, the fellowship, was sort of a limited time offer. And I'm betting that Google will probably still be there in 2 years if I, hopefully. I don't know. I actually really like the lab, and I'm very strongly considering applying for a research scientist when it comes time.
What classes do you take during your undergrad?
Which classes?
Yeah.
Yeah, so I took a bunch of physics classes, but my favorite classes were by far my computer science classes that I took. So it was this deep learning course. I also took the deep learning seminar, which at the time I think Don Sung ran it, and that was cool because we got people coming in from OpenAI and from Google coming in talking about what they were working on. So there's a seminar that's usually at the same time as the deep learning class, and I would suggest signing up for both. It's very minimal requirements for the seminar. And then one of my favorite classes was computational geometry. Love that class. It's coming up this spring. Jonathan Shuchek teaches it. He's a fantastic instructor and just a really cool human being. So those are by far my favorite classes. I also took a group theory for physics class, and that was really interesting. I love symmetry. Symmetry is just such a cool topic. I think James Analaitis taught it that year. I don't know if he taught that class again. But then I took a bunch of those standard physics things, so E&M. I took quantum field theory 1 and 2. Don't remember much from them. I just remember Peskin and Schroeder is a very difficult book to look at. So, yeah, sure.
The CS course that you were talking about deep learning, was it very mathematical or coding?
Coding. It's a lot of coding. So basically what you do is you get Jupyter Python notebooks that you have to fill in things. And you really need to spend the time doing the homework. That's the bulk of what you're going to get out of it. The lectures are really cool, and it's really interesting stuff. And they have guest lectures come in, people who work on TensorFlow and things like that. So it's a really, really good lecture format. But yeah, the homework takes a while. It's a bit of a commitment, but it's totally worth it because I use the concepts I learned every day. When I'm writing new types of networks, I need to code in my own you have a forward op and a back op. Normally you don't have to do that if you're doing standard things, but I usually have to write both, and so it's really good having had that experience that I'm not afraid to break open my neural network and scrap it to bits. So I think it's a really great class.
How do you think we convince more materials people to not be scared of going into the computational realm, and vice versa, trying to get more computational people interested in these kind of materials science problems?
Ooh, okay. So I think it's really hard to convince machine learning people to do anything but machine learning. I've talked with a lot of them, and it's really hard. So I think material scientists and chemists and physicists, we have to solve our own problems. Because part of it is you need the domain. Well, sorry, I didn't mean that in a psychological way. But
But also.
I mean this in an empowering way. I want to empower you to solve your own. I'll come up with another phrase for saying that. The reason I'm saying this is that all these scientific problems have a lot of context, and all those details are important. Think rotation symmetry and translational symmetry. These are things that we're well, yeah, duh, the equations have this symmetry. Don't you need it in your network? And the machine learning people are I think you just trade it on more data. I'm okay, well, we could, but we don't actually have a lot of data. And so a lot of our machine learning problems are very different in the sciences than sort of in industry. We don't have gobs and globs of data. Our data is expensive. We treasure our data. It has some problems. It's okay, and we need to nurture it and learn from it. So I'm not sure if that answers your question. I would just encourage you guys all to take that class, and then you guys should all come think about deep learning for atomic systems with me, because there's not enough people doing it, and I get lonely. So please come join. And you'll be so marketable just from taking that class, so you should do it anyway. It's just a good investment. So think about an investment portfolio. Yeah.
If we were thinking about taking that class, what kind of prerequisite knowledge would you recommend we have?
Okay, good. I would recommend being fairly comfortable in Python or one of the other bindings for TensorFlow, or so you don't have to use TensorFlow. You can use anything. Being fairly comfortable with code. Mainly, it's just being willing to put time for it. I actually do think that you don't have to go in with tons and tons of coding experience to do it. Familiarity with NumPy, or just any other matrix multiplication, review linear algebra. like remembering how to, when you do a matrix multiplication, do you do it this way or do you do it that way, and which dimension? Like basically all of deep learning is just remembering what's the shape of your multi-dimensional arrays. That's like half of it. Then the other half is a bunch of other stuff, but it's mostly just remembering that. So yeah.
You mentioned briefly having a background in architecture.
Yeah.
Did you ever want to pursue something that's not science?
Well, yeah. I mean, so what happens? I didn't know that you could major in architecture. So that when I went to undergrad at MIT, and they had an architecture program. They had a really cool architecture program, and actually that's where I got into all this geometric algorithms, because MIT has like a super architecture coding, like all the architects know how to code at MIT. It's really weird. So I didn't even know you could major in it. So I tried it and I was hooked. And so I was a double major for about a year. I was a double major in architecture and physics. There is no overlap of classes. I had a very full workload, and then I looked at senior year and I'm like, I'm going to take 2 30-hour studios in architecture. Like, this isn't going to work. And so I eventually dropped it to a minor. To which a lot of my friends in physics teased me, and they're like, you could have gotten a double major in math for like half the effort. Like, why didn't you do that? But yeah, I love geometry. That's kind of where I got the geometry bug, and it sort of followed me to grad school, and now I've figured out a way to kind of connect it all back together. So, all right, other questions? There, sorry, I think you've been waiting for a while.
What was the funding situation during your internship?
Yeah, okay, so while I was an intern, Google paid me. They also, yeah. It's a good financial decision to go work for Google as well, actually. So during my full-time internship, they actually paid me, and then they also paid me actually while I was part-time. So there was actually a period where I was on 2 incomes, which is probably the part that my advisor wasn't too pleased with. But I'm like, well, on paper, I'm 20 hours a week, Jeff. But that's how it worked out, just because I couldn't be at Google and have them not pay me. They have too much money. They just have to pay me.
So then Jeff wasn't paying you
during the internship, he was not paying for me. So it won't cost your advisor a thing, except for their complete fear that you're going to leave them. So yeah, internships bring up a lot of insecurities in advisors, and you just have to talk them through it.
Actually, I have a question regarding that.
Yeah.
How do we? So a lot of times, what happens is we'll have a talented student or postdoc who develops all of these skills in using machine learning and data analytics, and then they become so marketable to the industry that they're getting offers they can't refuse, and those offers aren't being matched at places like national labs and universities.
Right.
So we're losing a lot of the people who could make these scientific breakthroughs using these new tools, leaving. Do you have any thoughts on how we can improve the retainment?
Yeah, so I think sometimes getting them exposed to it sooner so that the sticker shock's not there, because the money will only enchant you for so long. And the perks will only enchant you for so long. So being there for 3 months, I was like, oh my gosh, this is the best place ever. It's like Disneyland, but like with a lot of computers and people who know how to program. And it was really great. But then, a few months in, I'm like, gosh, I miss this about the National Lab Sister. I'm like, oh, I wish I had someone to talk to about this. Or like there's a lot of software engineers at Google, which is great and it's immense, but like there's a lot more variety in an academic environment. So I think part of it, might seem unintuitive, but I feel like getting the students out there so that they sort of know the difference. Because I saw that sticker price. Like, I took a big pay cut to stay at the National Lab, but when it came down to it, I'm like, money's only going to make you happy by so much, and really being excited to be around like your immediate vicinity of people you're working with is going to matter a lot more. So I think that sticker shock has a lot less of an effect if you really see the difference in environment. But yeah, some people are also just going to leave because it also really depends on your situation, because some people are in situations where they can't say no to the money. It is a lot of money. And like, I don't, I'm not like, oh, like why'd they take the money? Like, it's a lot of money. But I think for some people, if you really like science, like you'll probably want to stay. Or you want the money.
I guess, even though I'm not really looking at machine learning, I'm interested in the arm of representation.
Sure.
You alluded to it a little bit. It seems like getting algebraic
Yeah, no, I think it's a huge challenge. And I want to, kind of back this out because representation kind of means a couple different things to me. So there's sort of like how you show your data to a network, like as an input. But then I feel like representation is also a matter of how does your network operate on that data. So there's sort of two components. And most people, when they think of representation, they think, okay, what am I showing my network? And then I'm going to use a standard network. And less often do people actually think about, okay, what if I change the network so that the way it processes the data is a little different, so that it sort of maybe has additional context about the problem, things like that. So I guess like there's things like attention models, which like if you have a sentence and you have a pronoun, like the thing that's important is whatever that pronoun's referring to, and so there are models where you can kind of see that the network has a bit of attention and like it'll attend to certain parts of the sentence that refer to another part of the sentence. But these are all things that are like, it's not just how they input the sentence. You can only input a sentence so many ways, but it's actually how does it operate. So I think thinking about network operations is a very important part of representing your data, because you're giving it additional context of like, I want you to operate on the data in this particular way. But I think it's a challenge, and you never know from first principles sort of exactly what's going to be best. So it requires a lot of experimentation. Because let's say you come up with the most beautiful representation, but your model doesn't train. That's a problem. And it maybe would have trained if we'd have a different way of optimizing these networks, but you'd have to figure that out. So it's sort of a bunch of things at once. So it's always experimenting, always trying toy models, always checking your understanding that this is actually able to learn the things you want it to learn. Does that answer your question? Or?
Well, it came up because we just ended the consortium on data analytics, and that's what people have done. And talk a lot about applying machine learning to data ingestion problems. Because they get all this unstructured data, they're really, like, they're just doing a lot of manual work. They're trying to come up with a better way.
Yeah, that's a super hard problem. That one I don't necessarily have much thoughts on, because I think just as it, me looking at my Dropbox at files I haven't seen for a year, it's hard enough for me to understand what my file scheme was, so let alone arbitrary, like unstructured data. Like that's pretty hard.
Okay, well it is 5 o'clock, so we don't want to hold everybody up. If you have more questions, you can come up afterward and ask Tess. But thank you for coming.
I have a beanbag in my office. Come visit.
Thank you, Tess.